Wanita warga India yang terjatuh ke dalam lubang benam berhampiran Masjid India di Kuala Lumpur dipercayai dihanyutkan oleh arus deras di bawah tanah. Ketua Polis Kuala Lumpur, Datuk Rusdi Muhammad Isa berkata, usaha mencari dan menyelamat SHR wanita berusia 48 tahun terbabit memerlukan perancangan rapi berikutan membabitkan infrastruktur awam.
Assalamualaikum warahmatullahi wabarakatuh and hello respected jury. My name is FARISHA binti ROSLAN, matrix number 2023686614, and I am here today to present about my final year project entitled The Identification of Sinkhole Susceptibility Hazard Zones using Random Forest in Kinta, Perak. So, what is sinkholes? Sinkholes are a depression or holes in the ground that often occur due to the dissolution of bedrock. They can pose a serious risk to both human life and infrastructure. This study focused on identifying areas in Kinta, Perak that are most susceptible to sinkhole formation using a machine learning approach, specifically the random forest. There are 7 condition factors were used in this study, which are slope, elevation, lithology, soil type, land use and land cover, groundwater wells depth and rainfall. The model successfully generated a susceptibility map divided into 5 classes ranging from very low to a very high risk. The results then were evaluated using the area under the curve and coefficient matrix, while for the model interpretation, feature impotences analysis were performed. Overall, this study presents an effective approach for sinkhole hazard assessment using spatial data and machine learning. However, despite these advancements, there are still gaps that need to be addressed. Many existing prediction methods fail to capture the complex interactions between geological, hydrological, and anthropogenic factors. In addition, based on Al Mahdi et al. 2020, some current models lack precision and do not fully reflect the spatial variation of sinkhole susceptibility. Furthermore, there is limited understanding of how conditioning factors contribute to sinkhole formation in specific locations like Kinta, Perak, which makes accurate prediction difficult. So this issue that I told you just now highlight the need for a more advanced data-driven approach, and that is exactly what the study aims to address using the random forest method. The aim of this research is to determine accurate sinkhole susceptibility hazard zones in Kinta, Perak using the random forest machine learning method. Kinta was chosen as the study area due to its karst landscape, which makes it vulnerable to sinkhole formation. And in order to achieve this aim, 3 specific objectives were outlined. First, to identify the key factors that influence sinkhole susceptibility in the study area. Second, to develop the sinkhole susceptibility map using the random forest method, which is known for its ability to handle large and complex data sets with high accuracy. And lastly, to evaluate the model's performance using validation metrics such as the receiver operating characteristic curve and the coefficient matrix. At the same time, feature impotences analysis were performed for model interpretation, ensuring that the predictions made are both reliable and meaningful. The novelty of this study lies in the integration of advanced machine learning with geospatial analysis to produce a more precise and interpretable hazard map compared to conventional methods. This enhances the effectiveness of disaster management and urban planning, particularly in limestone-rich areas like Kinta that are highly prone to sinkhole. For the methodology, this study began with selecting ArcGIS Pro software as the main software to process and analyze spatial data. The research was conducted in Kinta district in Perak, a non-limestone-rich area with a historical of sinkhole occurrences. 7 conditioning factors were selected and categorized into 3 main groups, which is geological factors, hydrological factors, and anthropogenic factors. All spatial data for these factors were pre-processed using ArcGIS Pro, and this involved converting the data into raster format, standardizing the resolution, and classifying each layer to create thematic maps for each parameter. Once all the data was prepared, it was used to train the RF machine learning model. RF was chosen for its ability to handle complex and its strong predictive power. The model was trained using known sinkhole location and evaluated through multiple evaluation methods. These include generating a sinkhole susceptibility map as well as conducting model evaluation using the ROC curve and confusion matrix. The performance of the model was measured using several metrics, including AUC, accuracy, and precision. Finally, a feature importances analysis was conducted to determine which factors contribute most significantly to sinkhole susceptibility, helping to interpret this model result in a meaningful way. The results of this study are presented in three main parts. Firstly, thematic maps were generated for each of the 7 causative factors. These maps help visualize the spatial variation of each factors across Kinta and reveal patterns that are commonly associated with sinkhole development. For example, areas with steep slopes and high rainfall levels often coincide with locations where sinkholes have previously occurred. Two of the parameters, elevation and slope, were derived from a digital elevation model, or we call it as DEM. The DEM provides a 3D representation of the Earth's surface. And from this data, I was able to generate a slope map that shows the steepness of the terrain and the elevation map. The rainfall data was obtained from the Department of Irrigation and Drainage. In the pre-processing phase, I first averaged the daily rainfall values from each station into monthly average. Then, these monthly values were further used to calculate the annual average rainfall for each of the 20 rainfall stations of a 10-year period. After that, I used the kriging method and the spatial interpolation to generate a rainfall distribution map based on the average daily values. This technique helped visualize how rainfall is distributed across the study area. The lithology thematic map displays the geological formations present in the Kinta district, which significantly influence sinkhole susceptibility. The area is primarily composed of limestone formation, especially in the central and northern parts of the study area. Limestone is a soluble rock that dissolves easily when exposed to the water, making these regions more prone to sinkhole development. Other formations such as schist, granite, and alluvium were also mapped but were found to be less associated with sinkhole occurrences. By visualizing the lithological distribution, this map provides a clear understanding of which geological zones are most vulnerable to sinkhole formation. The Land Use and Land Cover (LULC) map shows how human activities and surface cover types are distributed across Kinta. Categories in this map include urban areas, agriculture, forests, mining land, and water bodies. The result shows that many sinkhole-prone locations are situated in agriculture. This land use may contribute to increased water infiltration or changes in underground pressure and accelerating the risk of sinkhole formation. The map highlights the impact of anthropogenic activities in increasing susceptibility, making it an essential factor in risk assessment and future land use planning. The soil type data used in this study was obtained from open source geospatial databases. The thematic map illustrates the distribution of various soil types across Kinta, Perak. Different soil textures such as clay loam, clay, and sand clay loam were identified in the area. These soil types vary in terms of water retention and permeability, which can influence the rate of groundwater infiltration and underground erosion. The second result is a sinkhole susceptibility hazard zones map using the trained random forest model. This map categorizes the study area into 5 susceptibility classes, which are very low, low, moderate, high and very high. The output showed the Bandar Ipoh falls under the very high risk zone, while a parts of Mukim Kampa are classified under the high susceptibility category. These findings are consistent with historical sinkhole reports and validate the spatial accuracy of the model. Lastly, the model was evaluated through 3 key methods, which are the area under the curve ROC, AUC-ROC, achieved a value of 0.91, indicating that the model has strong discriminatory power in area, distinguishing between sinkhole susceptibility and non-susceptibility areas. The conversion matrix shows a high classification accuracy of 90.7% with precision at 89.3% and recall at 92.6%, a false positive rate of 11.11% and an F1 score of 19.9%. Additionally, the feature importances analysis revealed that the rainfall, elevation and groundwater well depth were the most significant contributors to sinkhole susceptibility. This highlights the crucial role of hydrological and topographical factors in triggering sinkhole formation in the Kinta region. This study is significant as it aligns with Malaysia's National Policy on Climate Change (NPCC) by addressing geohazard issues, particularly sinkholes, which are becoming more frequent due to environmental changes and human activities. By identifying high-risk zones, these research promotes sustainable land use planning and enhance preparedness against geological hazards. Furthermore, it also supports the achievement of Sustainable Development Goals SDG 11 and 13, which focus on building sustainable cities and communities, as well as taking urgent action to combat climate change and its impact. So as a conclusion, this study successfully maps sinkhole susceptibility hazard zones in Kinta, Perak, ranging from very low to high risk. Very high risk. The feature importances analysis showed that the rainfall was the most influential factor in sinkhole formation, while soil type had the least impact. The resulting hazard map revealed that Bandar Ipoh is a very high-risk area, with a part of Mukim Kampa also show high susceptibilities to sinkhole occurrences. The RF model used in the study shows strong predictive performance, achieving an AUC with an overall accuracy of 90.7% and the precision. This finding confirmed that the model's effectiveness and reliability in identifying sinkhole-prone zones, supporting its application in future risk planning, mitigation efforts, and decision-making processes. That is all from me. Thank you.